Welcome to another one of our live events, this time with myself, Jamie Turner. I'm Technical Development Director at SMD, and we're talking today about welded shear studs in composite construction. It's quite a common topic on the Technical Helpdesk, hence why that's been chosen. So it's great to see so many people register for this webinar. And I know we've got people from all over the world, and that's good to see. So welcome if it's your first one. Without further ado, we'll continue. Just a couple of points to point out before I forget. During the slides, we will point to guidance information and documents that we have as a business. And I know Pete is on hand to link them in the chat so you can get access to them easy. Also, if you have questions, I'm quite happy for you to ask them as we go, and I've got other colleagues looking out on the chat, or whether you want to actually unmute yourself and ask, then happy for you to do that as well. So we'll begin. During the presentation, you'll see these orange tabs in the bottom left-hand corner. That is links to our TGN Online website. So a lot of the information I'm going to talk about today is available there. This will just give you pointers to where it is, so it's worth looking out for those in the bottom left-hand corner of the screen, should you then want reference to those in future. So what are we going to talk about? I mentioned it's welded shear studs, but in what content? So I'm going to just briefly mention about the specs, shear stud specification, codes and the like. Then designing shear studs in a composite deck, so a bit on figuring out resistances and how those resistances are used and how deck impacts on them. Why spacings of shear studs are so important with not just our products, but any composite deck products. Then a bit on the welding process. So how do we install the studs? But that's going to be a very kind of concise section, because we will have one in the future about planning and carrying out welding. More the installation side of things will be a future CPD. And last of all, just finishing off with some practical considerations and a few other options that are out there. So to start with shear stud specification, so the studs we're talking about today are welded shear studs. Those of you, I'm sure a lot of you know what they are, but if you don't, this is studs being welded to a beam through, in this case, our R51 decking. So that's what we're talking about today. So the specification of a shear stud, what shear studs are they, where do they come from, what do we use? The specification of shear studs, the product itself, is from BSEN ISO 13918. That's the image you see on the right hand side, and the studs that we use in terms of welding to steel are ones with a flux ball on the end. So you can see this A parameter here. The type is called an SD1 type, and then the welding of the studs is carried out in accordance with BSEN 14555. 14555 has a wide range of application. It's not just about shear studs in construction, it's stud welding for all manner of things, from automotive to construction. So it's important that you reference the right aspects of the code. I mentioned we're focusing heavily on construction and composite construction, so that's the SD1 type. Bit of material information there. The key thing is that the ultimate tensile strength of the shear studs is 450 for the purpose that we're using them and that we require for composite beam design. And the ferrules that are used with those shear studs to weld the stud to the beam, whether that be through deck or direct to beam, is a type UF. Again, that is detailed in the standard, but you can see one in the image on the right there. So we're talking about a welded shear stud. There are a number of diameters available and also a number of lengths. I'm focusing very heavily here on the studs welded within our products, so our deck products. So typically you would be using a 19mm diameter shear stud with the head and etc. The burn off of a shear stud varies depending on how you're welding to the beam. So pre-weld, the stud will be longer than after weld, and the important thing to note is if you're welding direct to a beam, the burn off will be less than if you weld through the deck, purely because of the amount of protrusion that you need to burn through the deck and then into the beam. So at the bottom here in this table is information showing with our products. R51 plus a 95mm after weld stud is used. TR60 is typically 95mm after weld length, and TR80 is 120mm after weld. The lengths before weld are notably longer than that, for the reasons I mentioned about burn off during the weld process. And it's just important to note those two differences and making sure that the right studs are being used. We have heard stories in the past of studs shorter than 105 in pre-weld being used for through deck welding. Then you don't end up with your 95 length after weld, which is can be quite critical. So that's just a bit on the stud spec that we're talking about and kind of referencing today. So now more onto the design of a shear stud and what does a shear stud do in composite construction, so for composite beams and in composite deck. So what does it do? The shear stud is welded to the beam, in our case, or in composite construction with metal decks, through the deck typically, and that stud transfers force between the beam and the concrete slab to create a composite beam. So in the construction stage, we're putting a deck down, we're welding the shear stud through the deck, and that beam is then supporting all the load of the concrete going onto the deck. Once that concrete is then hardened, the beam is working with the concrete. So in the red shaded area, that has created effectively an extended top flange to the beam. That beam using that concrete with the beam, because we've connected it with the shear stud, will then support the loads that are applied to the slab during the life of the building, the use of the slab. So what the shear stud does to transfer that force is when you apply the load to the slab, so here we have a slab on a beam between two supports, and as the slab goes in and beam goes into bending, you get slip at the end of the beam, and that basically puts force at the interface between the slab and the beam. So if we had no shear studs at all, that slab and that beam would be able to act independently to each other. By putting shear studs in, what you create is a resistance to that slip, and what you get from that is then the beam force in one direction, the slab force in the other, and the shear stud is what then transmits the force between the concrete and the beam. So in this close scenario, you can see there the point at which the stud is there pressing against the concrete. You get concrete in compression and you get crushing locally in that area. And I'm going to talk a bit more about that in a bit. I noticed the hand's gone up. By luck more than judgment. If you've got a question, Chris, I see.
Sorry about that. It was just about the with it working together. I take it that the neutral axis goes up into the flange, doesn't it?
Yes, depending on your slab.
Yeah.
Depending on the materials, yeah, your neutral axis moves. Correct.
Yeah. Sorry about that. I'll shut up now.
No, that's all right. No, it's important that I mention these things. So that's good reminder. Yeah. So the neutral axis does move, and the composite beam, which I'm not talking about composite beam design as such today. I'm talking about studs. But the composite beam design in Eurocode 4, as you say, it shows where the stress block is, where the neutral axis moves, and how that impacts depending on where the neutral axis sits as well, once you've got the two materials working together. So yeah, so that's what the shear stud does, and I'm going to talk a bit more about studs failing and the resistances of now. So kind of focusing heavily around that, and these are snapshots from aspects of the code. There's obviously a lot more to composite beam design than just shear studs, but shear studs is kind of a key aspect and something that there's a lot of questions about, hence the focus. So how does a stud fail, and how do we then design for that failure resistance? So in the code, there is essentially the way that a shear stud resistance is built up is determining the shear stud resistance as if it were in a solid slab. And then, sorry, my phone's on silent. Sorry about that. The shear stud resistance as if it's in a solid slab, and then once you've got that resistance, you then look at the deck and how that deck impacts on the stud resistance, because we then have essentially not a solid slab. So first of all, you need to determine the resistance of the shear stud in a solid slab, and we do that by two equations from the code. And those equations are essentially saying, this top equation here is all related to the steel aspect, so the strength of the shear stud, the diameter of the stud. So it's more talking about, have we got a failure in the stud connection itself? The second is in the concrete, so it's related to the concrete compressive strength and to do with essentially the cone of failure that you would get. So by carrying out these two equations, you then, whichever is the smaller, will give you the resistance of that shear stud in that slab for those particular criteria, depending on the size of stud you're using, etc. What I would say is, and you'll see from some photos later, with 19mm diameter studs in the form of construction we're talking about, it is nearly always, and I think almost always, in the failure is in the concrete, not in the connection between the stud and the beam. And you can kind of deduce maybe why that is as we go through. So talking about how does metal deck affect the stud performance, and me mentioning there that it's very much in the concrete failure. As you can appreciate, if we have a solid slab, you would see something like this, the beam running left to right in these images. So in a solid slab, you have a cone that goes right the way down to the base, so you have a lot greater shear surface in the concrete than you do if you then have that within a deck, because obviously at some certain points it will impact with the deck itself. So that's kind of an important thing to think about, because you now have a lesser concrete shear surface as the slab and beam move in opposite directions to create your stud resistance than you would for a solid slab. So that's why we work this factor out. We then reduce the resistance based on the deck profile being used and stud being used. And that's where we're going to kind of move on to a bit now. So how does that metal deck now affect the solid slab stud resistance? So the code, and this is all Eurocode 4 references, as you'll see from the bits down the bottom here. So the code utilizes the profile height, the trough width, which depending on your profile type is either your average width of the trough that the stud is welded in, or the thinnest width if we have a re-entrant like our R51 plus profile. So those two are very much about the geometry of the profile and how much concrete do you have around the stud. It's then about the stud height, so what protrusion do you have above the deck, and the number of studs in a trough, which does surprisingly impact considerably the reduction factors. And I'll talk a bit more about that in a moment. So this equation here is just one of the equations from EC4 with regards to how you build up the KT. So the KT is the reduction factor that we're then going to apply to the solid slab stud resistance to get the stud resistance within that given profile for that given concrete and design. There's loads of
Jamie, sorry to interrupt.
Yeah.
I don't know if you can hear me. There's a question just being posed. Is there any benefit in the length of the stud increasing with the slab thickness, or is this only dependent on the profile depth of the deck itself?
Interesting question. There is.
That's from Kieran.
Limit, and I haven't got the numbers off the top of my head. Up to a limit, there is benefit, and clearly there would be benefit. I think what I would say is the code, and due to how I guess composite construction has developed, the types of studs used, the fact that slabs are typically shallow, once you get above a certain value, and we're talking really about 100 mil stud for a TR60 plus or an R51 plus, whilst putting a 120 or a 130 stud will clearly give you more resistance, the codes are very much heavily based on testing, the primary amount, if not most of which, is based on a 100mm stud. So there isn't, you're kind of going a little into the unknown in terms of being able to have a equation that could give you the values for that. Now, that's not to say that you couldn't test some, determine what that is, and then ultimately apply a better resistance, but it would require work beyond the standard as it sits. So as the standard sits, there would be no benefit in having a longer stud, although if you think of the theory, then clearly there would be a bit more, but as to how much, it's not necessarily quantifiable in the code. I hope that helps. There is more quite advanced information in P405, which is an SCI publication, and that gives you more guidance on where you can put the mesh. So it gives you resistance values for mesh low and high in a slab. Typically in the UK, we tend to put it high in the slab, but you may wish to increase resistance by dropping the mesh lower, which can give you some improvement in KT values. So KT values are, as I've said, the reduction factors, and this here is just a table that shows the reduction factors for our products, and this is all available on our TGN online site. So this is actually a crop from a guidance document that we've sent out. So the bit I'm really talking about here is this table, and the important part in this scenario is to kind of raise, I guess, or highlight, is that two studs doesn't equal 2 times 1 stud resistance. So to best show that, if you look at 1 stud per trough in a TR60 of less than 1 mil, we get 0.85. That's the reduction per stud. So it's not far off of a stud in a solid slab. If we move to 2 studs, because of the limitations in the code of how far the studs have to be apart, we only get 0.49 per stud. So 2 studs in a trough at the very closest center in the code, which I'll come to in a moment, will only actually give us 0.98 in comparison to 0.85 of 1 stud. And I think that's quite important to realise, that putting 2 studs on doesn't give you double 1 stud. And I'm going to move on a bit more onto that in a moment, but this was to just put some numbers to that. The value engineering guidance sheet that we send out when there's value engineering options on a job, we always send this information out at that point anyway. So that information again is available on our website and on TGN as well. Sorry, more phone calls in the last 10 minutes than I've had all day. So using the shear studs in design, and that's kind of leading on from the KT factors. The designers of the composite beam, and I know some of you out there will be designers, will use a design standard. So in the UK, typically that'll be Eurocode 4, or it may be BS 5950. They have calculations for stud design resistances, which we've just seen the ones for Eurocode 4. And those, as I mentioned, code equations are based on certain testing, industry testing. Some of that's collaborative industry testing, some of it will be individuals testing. So this picture on the right here is a picture of a test that we had on a previous product of ours. And it shows, you can just about see the 2 shear studs here, and then this cone of failure that I kind of showed it the other section on earlier. The important thing about the rules that are in the code is that they do have boundaries and conditions involved. So where the question I had about a longer stud, the boundary involved in the code and in the tests that have been carried out is kind of the 100mm stud in an R51 or TR60, or not far different to that. So that's why going above 100mm, the guidance is less, because you're kind of going beyond the boundary of the testing that's been carried out, and standard practice in the UK for that matter. The design rules have minimum spacing requirements outlined, and that's minimum spacings between studs to the slab edge and many others. And that's what I'm kind of going to talk about in a moment. And to understand why spacings are so important, I'm kind of going to take you back to what we said about how studs fail. If we appreciate here that a single stud, we saw, okay, it looked like that. The cone of failure looks, it's not quite 45 degrees because you get an extension created by the trough, but the principle is that. So 76 is the minimum between a pair within the standard. And obviously, if we put studs closer than 76 together, then you reduce the concrete shear surface that the stud would fail in. By pushing them 76 apart, you're increasing the concrete shear surface by this middle area. And obviously, the further you increase those, the better the stud resistance will be, until you get to a point where they would actually act isolated. But in reality, a pair would normally be put at minimum of 76 apart, because that is the code minimum. So typically what the steel beam designer will have based the designs on. And also, trying to push these too far apart, often the steel flange wouldn't actually be big enough to position the studs where you need them. The important thing, though, is to notice if the incorrect spacings are installed, it will reduce the resistance, and you could potentially, although there's safety factors involved, you could potentially be looking at a safety issue if the minimum dimensions aren't observed. And this is again that test, and you can see where the slab's been peeled away, just to give you a bit of a picture of how it would and does fail. So understanding that spacing limits and considerations are important. This is just a brief overview of the outline limits on stud position along a beam. It's kind of a 5 diameter, so it's all related to the diameter of the stud. 19 millimeters is nearly always what we use. You can through deck weld 22 mil diameter studs, but the design benefit of that is limited, so 19 millimeters is pretty much the go-to always, both for the TR6 up to TR60 deck, and TR80 deck is 120. So, but they're all 19 millimeters. A few key things.
Jamie, apologies. I was just on a call. I just missed another comment that's come in.
Yep.
And the question is, does this mean that the increase in capacity can come from increasing deck thickness and concrete class?
The increase in stud capacity, yes, there is an increase. Yeah, so if I will zip forward again, you can see here the increase for deck thickness is incorporated in the factors here. So you can see once you get above 1 millimeter, the factors do change. So with certain profiles, it all comes down to the equation. But yeah, principally the answer to that question is yes. If you up the grade of concrete, obviously your shear surface area is the same, but the resistance within that shear surface is higher because of the higher concrete class. So you could up the concrete class, or yeah, thicker deck would give you a greater KT factor. And that is why in this sheet I show on the right here, that is why we give this value engineering guidance sheet out, because if someone is trying to value engineer from a 1.2 to a 0.9, let's say, if they've utilized 1.2 and that's quite important in the shear stud resistance, then a 0.9 may not work. It's just that's kind of what this sheet is all about. But yeah, the answer to the question would be yes, up in the concrete or up in the deck thickness will increase, although not massively, it will increase the stud resistances. I hope that answered that. So yeah, just a couple of key other limits are the minimum distance between the stud and the toe of a beam. That is 30 millimeters. So that's the center line of stud to toe of beam. So that also limits the flange sizes or the minimum flange sizes you need. Top cover recommended minimum is 15 millimeters or 20 millimeters if you're protecting against corrosion. There are instances where you can go below that, but that is the recommended minimum. And usually your slab depth will provide that because your fire rating for the slab governs the slab depth rather than the stud length itself. And the key one to make note of is that the flange thickness must be greater than 0.4 times the diameter of the stud. which for 90 millimeters is 7.6 millimeters. But an important thing to realise is you may end up, if you're designing at the very lowest thickness of a flange, you may end up, due to the temperatures involved, etc., in the weld process, you may end up with that then having damage to the underside of the beam to repair or make good or be touched up later. So it's an important consideration, and as you can see, 11.7 in TGN gives you a bit more info. You'll see this photo and a bit more on that subject. So we've talked about kind of the general spacings, and I just wanted to run through those on our products and what that means. So there's a number of things that the profile influences in terms of what you can and can't achieve with shear studs on a beam and shear stud spacings on a beam. One is obviously the deck orientation. So if you have a change in span, like we see here, the deck running left to right on the left of the beam and into the page on the right of the beam, then you can only put studs at 333 centres for a TR60 plus on the left of that beam. On the right, you've then got flexibility of where you can put those studs. So the number that is required is more achievable in this scenario. However, you will have different resistances on different studs. So if you were getting into the complex design of this particular beam, you would have a different resistance here than you would here, because this is more like a primary beam scenario. This is a secondary beam scenario, because the deck is coming into the beam. Just something important to consider. Obviously, beam softwares, etc., will consider a lot of this anyway, but it's important to understand what can be achieved. So the obvious one is on a secondary beam, so a beam that is perpendicular to the deck ribs, is do the stud centers suit the profile geometry. So this is just a couple of images. This is our R51 plus profile. Studs at 150 centers are achievable, 150 or increments of. And then with our TR60 or TR80, you've got TR60 at 333 from stud to suit the center of the rib positions. And with TR80, it's 300. So it's important that you are designing the beam for the right stud centers for that product. And that then, at butt joints where you're staggering, will govern your minimum flange size unless you go into having pairs or more different stud situations. So yeah, are the beams wide enough? And this is what I meant by that. So you've got a single stud. The beam effectively could be 100 millimeters wide, but typically we would always say 120 millimeters is your minimum requirement, because somewhere on a job you will need butt joints like this, and the minimum rules then govern that you need a 60 mil bearing on either side, because you need 30 between the stud and the edge of the beam and 30 between the center of stud and the end of the sheet. And that's if you're using the deck as transverse reinforcement in your composite beam design. So the important thing is minimum 120 mil flange for decks, really. That is the recommendation. As you then go up with different stud arrangements, 2 studs or more, the minimum beam width obviously widens, because the minimum space between 2 studs we saw earlier was 76. If you add the 2 30s onto that, that gives you a minimum of 136. So your beams need to be wider. So it's important to understand how wide the beams need to be to facilitate the stud numbers that you need for your composite beam. Then we've got primary beams. Primary beams are less of an issue in terms of the longitudinal spacing. The challenge is more ensuring that you can get the studs onto the flange through a flat in the profile. So we do that by obviously firstly iterating and looking at the optimum setting out for the profile, and if we can, avoiding the need for flashings, but in many instances you can't avoid that. So we would then use flashings, which in this image is shown blue, where you would cut back the profile, flash to the beam, you can then get your studs on, and obviously the flexibility on a primary beam is a lot greater anyway, because you don't have the impact of ribs across the beam. And you also, or we may have a, rather than actually cutting the profile back like that, we may be putting just a Z profile on the very edge of a sheet just to close off that edge, similarly giving you the ability to weld to that edge beam or internal beam if it's in an intermediate primary. Just a point to note, and this is more likely at edges, but also you can have it at internals, that studs may need, due to the profile setting out and due to slab edges, to be off center. So there are instances where the studs have to be welded off center of beam, and that is very common, I would say, because it'd be very difficult to achieve at the center of a trough on every beam. So it's common to see studs off center, particularly at edges where there's a minimum dimension to the edge of the slab if the edge beam is designed as composite. That was very much about kind of our products, and I wanted to talk specifically about TR60 plus our trapezoidal 60mm profile, because it's the one, what should I say, it's the one product group in the industry where different products have different centers, and that obviously then for a designer or someone wanting to purchase needs to be aware of the considerations involved in either what to specify first, whether they want to change specification, etc. So this was just a slide to show that our TR60 Plus is a 333 pitch profile. Others vary from 300, 323, but as you can see, there is a slight difference. I just wanted to kind of discuss that briefly. I thought best to do that through just a quick lookup of a design. Obviously, depending on the design scenario, the picture may look slightly different, but the important thing I think is this was a 9-meter secondary beam, so a beam with ribs running perpendicular to the beam. Sorry, with deck ribs running perpendicular to the beam center line. 3.5-meter deck spans either side, which is relatively common. A 130 slab. A 130 slab, C2530 normal weight concrete slab, and 0.9mm deck, and just office loadings. And what I really wanted to do was just get the picture across of what to consider and how to consider when there is a need to change. So the number of studs, because of our trough centers, you would get on that beam would be 26. On others, so I've gone to the lower end, so you've got a 300 and 333 are kind of the limits. There would be 29, so you'd have 14 in half the beam or 13 in half the beam. The KT factors for both profiles are very similar, slightly different on pairs, but not hugely. So I just wanted to give a picture of them. What does that mean in terms of the shear resistance for that beam in half of the beam span? And you can see, because you can get more studs on at 300 centers, you end up with a higher shear resistance than you do with 333 centers, but your shear connection is still well above the minimum requirement that was required in this scenario. So with less studs, with less deck material, because our 333 trough product has slightly less steel than the 300, with less studs, with less deck material, you're still achieving design pass in this scenario, and that's the case for many situations. So by using TR60, you're actually looking at a reduction in raw material, which can lead to potential program and cost savings just by a small number of studs. Obviously, less studs to install, less studs to weld, and a slightly less area of deck involved as well. Just worth considering. There are instances, so this is what I wanted to lead then on to. There might be instances where, because of those extra few studs, it will work with another product and not at 333mm centers. And there's a number of answers to that. It's not common that is an issue, because they're quite regularly governed by serviceability, the beams, depending on your lengths and your loads. So there are cases where it may be. The recommendation would be design initially with the worst case spacing. So in this scenario, it'd be with a TR60 Plus, and that then gives you the flexibility should you wish to change spec later. Or the other option is if you're maybe looking to change to TR60 plus from 300 pitch, you've got options where you've got certain beams that are a problem. You can look at pairs, for example. You can look at irregular stud patterns, so we can pair up at certain ends, or alternate pair single, just to build up that additional shear resistance in the beam. There is a lot of information on the partial utilisation of beams and shear connection rules back in that P405. I also would point you to this if you don't have like one of the industry standard kind of beam design softwares. There is a composite beam checking tool available on the steelconstruction.info site, which allows you to kind of just do some quick single beam calcs for checking the whole beam, but specifically if you wanted to play around with shear connection numbers, it gives you the shear connections similar. It would give you similar values to the calcs that I've done here to give you these values at the bottom, and also it will give you the shear connection rules required. So I think in this design scenario it's 25% from memory. That is, you can obviously run those for yourself.
Jamie, quick question.
Yep.
I think Pete may have also just provided some guidance, but I think there's a two-part question here. Is there any guidance on the minimum stud requirements to provide lateral restraint to the beam, assuming there's no requirement for the slab to act compositely with the beam?
The minimum stud requirement for lateral restraint.
Yeah.
So lateral restraint of the beam in the construction condition, I assume we're talking about. I'm guessing. Well, yeah. The lateral restraint rule is about the percentage of force in the compression flange. So there's not any guidance as to how many shear studs are needed, but essentially you could work out the stud resistance and compare that to the force in the compression flange of your beam. So I would suggest it wouldn't be that many, but there is a limit on the number of the spacing of studs top end as well as bottom end. So you can't go closer than a certain number, but you also can't go any further apart. So typically what you see is studs at around 600 or 666 to suit the profile centers when they're being used for other purposes and not necessarily composite beam design. But to think about beams that are where you've got lateral restraint to the beam without composite beams, often the lateral restraint is provided by a more robust fixing to the deck. So
that was the second part of the question, actually, because it says for the metal decking to provide lateral restraint to the beam, is it a must to use welded studs, or shot fired fixings will be adequate? And
you can, so it comes back to the compression, the force in the compression flange for your given beam scenario, but you can achieve that with Hilti EMP nails, which, to give you an idea, an EMP has about 5 to 6 times, 5, 6, 7 times the resistance of a kind of a multi-purpose nail, which are kind of the temporary nails that we install. There is a link on TGN for lateral restraint, and that's actually got the resistances provided by the different fixings. So if you go into TGN and type in lateral restraint, then it will give you a bit more information on that. But yeah, so if you want lateral restraint for the beam, it isn't necessary to have welded studs in all cases, no. Hopefully that answered that. So yeah, so that's kind of all the design aspect of the presentation. And I was just going to now run through a bit on the welding process, relatively quickly skirt over this because there will be a more in-depth presentation coming on installation, planning for welding and all the kind of concerns and considerations involved. We ourselves have a fleet of mobile stud welding units, so this is 2 of them traveling around the country onto sites welding shear studs. There are other options. That is 2 of the welding sets that we've used. The ones on the right I think are now defunct, if I'm honest. Now Weld 6000s are fairly common in the UK, and you can use other other power supplies, so you don't have to have our mobile rigs turn up. You can have site power, you could have a generator, static generator on site, but you do need the 415 3-phase 125 amps per phase requirements, and we have a guidance document on that we provide on jobs so people know what we need and when. So that's the power needed. We also ourselves have developed welding procedure specifications, so this just provides guidance on the setting ranges to be used. So you should have a welding procedure specification, that's a requirement of 14555, and that will tell you a range for the welding current, the welding time, the protrusion and the lift. So that will be a range that you have to work within on any given day. And we have these WPS, as it's called, for 16 up to 25mm diameter studs, because you can weld direct to steel, and we have them for direct to steel. We also have them for both a standard coated deck, through deck, and a HD coated product. So HD is our high durability deck, so it's got a better coating, which means the coating's slightly thicker, which means your settings have to, in generally, be slightly different. So we've got qualified welds settings for that. The tool you're using, so we've seen the set at one end, the gun at the other end. Those that have seen welding already will know it, but that's kind of just the gun and the parts of the gun, just for a quick look up. You can adjust the protrusion and lift at this end, and the key thing is the protrusion beyond the ferrule at the end is essentially the part of burn off that you will ultimately see going into the flange of the beam. So the drawn up weld process, using that gun with the chuck of the gun at the top here, you have the ferrule laid out, you have the stud position, the stud is loaded into the gun, positioned against the base metal. When the trigger is pulled, it pulls the stud away, which is the lift, that kind of the lift setting. That lift ignites the arc. The arc then ultimately heats up the top flange of the beam in like a molten weld pool, and then, for want of a better word, brute force straight down into that weld pool, which ultimately then creates your weld, and the ferrule is what then contains the weld around the foot of the stud. And it should look something like that, but in reality, that's a nice image. In reality, it will look something more like that. That is from one of our weld tests where we had macros done on them, just to see how it would look and to make sure it's not over porous in the weld. And that's just an example of that.
Jamie, another quick question. It's probably a slide previous. There's a myth that the thinner gauges can get easily damaged when handled on site, and the galv coating comes off easily. Is this nonsense?
You can answer that as well as me, Dan, I think.
Yeah, I was going to say the fact that yes, in part, anything that's a thinner gauge will, by very nature, have less material in it, so is more prone to damage. In terms of the galv coating, the method and application that galvanized is applied to the sheet material before it's made into decking is such now that it doesn't come off, to use that question. It's more integral to the base material than it probably maybe was previously in years gone by. Certainly when, if some people might remember, the G600 coating, which is a very thick coating galvanizing, where the increased durability was achieved by just putting a lot more galvanizing on the base material. That does have a tendency to crack and flake once you process flat sheet into corrugated and bent material. That hasn't and doesn't get used at all these days. So in terms of the galvanizing, it's robust in terms of its adherence to the base material, and it's the only damage you're likely to get is the thinner gauges can be more susceptible to bumps and drops if you drop something heavy on it, like maybe a beam or a heavy piece of equipment.
Yeah, that was exactly what I would have said. I don't think the galv will break off, but naturally being thinner, it could get damaged easier. But that's not something that commonly happens, because at the end of the day, if you drop something relatively heavy on, whether it's a 0.9 or a 1.2 mil thickness, the deck will get damaged. So it will be slightly more susceptible, but I wouldn't necessarily say vastly more susceptible to damage. And certainly the galv damage issue I've not heard. The only point you sometimes could get an issue with galv would be in the actual manufacturing process, but that's something that needs to be controlled in the factory and not a site thing. So that's the weld process, and then I'm just going to talk quickly about tests. So pre-start, how do we make sure the studs provide the weld that we need and give then hence the resistances that we talked about earlier in the presentation. So you start with what's called a WPQR test. That's 10 studs welded and bend tested to 30 degrees. That determines essentially your settings for the day within the ranges that were in the WPS that I talked about earlier. So that will give you your amps, your time, your protrusion and your lift settings. You'll record them on a drawing and you'll carry on with your shift on the basis the 10 studs welded and bend tested have passed the 30-degree bend test. If they fail, you obviously change your settings until you get settings where the consistency of the weld is good enough. And typically that will be good enough nearly first or second. Usually you don't need a lot of moving the settings around, purely because the WPS has pre-qualified those. And that information should always be recorded on the handover, or it may be on a marked up drawing. So you can see we have a section on our handover for weld settings used and the location, and you can also mark up the drawing as well. Different people do it different ways. So that's the testing for, okay, what settings do I use today? You've then got, okay, are the settings I'm using continuously working during my shift? So that's what's called the product surveillance testing. So it's just monitoring that the works are going ahead and the studs are continuing to weld to the beam as required. So there's 3 test processes in that. Visual, so you break the ferrule away and inspect the weld, like in this scenario. Ring test, so the second stage, which I didn't have an image of, it was basically, if it was, it would be someone hitting a stud with a hammer. So you basically go around every stud, tapping it with a hammer, and you get a ring, shows it's passed. A dull sound is when there's kind of porosity or fracture in the weld, and often if it's a really bad, if it's not the weld's not taken, then you're hit with a hammer and you can break it off with the hammer, which clearly you wouldn't be able to do if the weld's taken correctly. But ultimately, if you get a dull sound and it sounds like it may have failed, you should always bend test that stud, but you should also bend test at least 5% or 2 studs per beam as a minimum. So bend testing for production surveillance is only to 15 degrees, not the 30 for the WPQR. At 15 degrees bent, you then leave the stud in that position. You do not bend it back, because obviously that's just creating extra force on the weld, and ultimately the 15-degree bend isn't reducing the height of the stud that much in terms of its geometry. So you can just see an example here of a welded stud, a bend tested stud. If you get no fracture on bend, that's an acceptable weld. If you get a failure, you then test adjacent studs to it to make sure they haven't failed, because you're trying essentially to just figure out where the problem is. Is it just that one stud, or is it maybe a few more? And if you get further failures, you then have to go back, look at your WPQR, and maybe reassess the settings accordingly. Just like for information can be shown on a drawing or on the handover sheet at the end of the works. So what can affect those settings? What can affect the weld quality? What might cause a stud to fail in terms of the weld itself? So you could have paint or contaminant on the beam, between the deck and the beam. Wet weather, hasn't dried out, hasn't been dried off correctly. What they call as in the industry is deck lift. So that's basically air or a gap in between the deck and the top flange of the beam. So that can create, as you're welding, obviously more porosity in the weld that essentially then causes failure when you test the weld. Could be to do with the welding set and equipment. So that's why the WPQR is really important. Interference from other welding activities can have an impact. And also things like steel connections, which ultimately are part of the circuit of the whole welding process. If you've got stuff at connections that could break that circuit or cause a problem, then it can have an impact. Not that common, but can have an impact. Most importantly is the making sure there's no paint or contaminant on the top flange, because that in itself will cause all sorts of problems. That's why unpainted top flanges are a must. And that's just a picture of a just a number of studs, and you can see visually there that they all the welds are okay, or someone who's aware of what a weld should look like. This is just the last couple of slides now to finish off. A couple of considerations practically. So you saw the gun at the start. The gun has obviously got a minimum size, and the stud has a minimum length. So you need to make sure if you're designing composite beams, that you can get those studs on site. So if you've got a beam over a beam, like in this scenario, you need at least 550 millimeters for a 95 length after weld stud to enable that to physically be put on. There's other ways of putting studs onto top flanges, not using the stud welding gun process, but that will be a bit of a pain. So the better situation in that scenario is to design the bottom beam as non-composite or pre-studded in the works, or different way of providing those studs in that scenario, if the dimension is quite tight between the underside of the top beam and the top of the bottom beam. The other thing is that crane infills or temporary hoist infills, that kind of stuff. So often that will impact more on the works this is more on the installation. You can only weld one side of the beam. You then have to weld the other side once the crane or the hoist is removed. So it's just thinking about what do you weld, when do you weld it, and where do you put your day joint, so such that the studs aren't being put under load before the beam has its full number of studs. And just some other applications where we ourselves have provided studs, but it just gives you a flavour that it is still construction-ish, but not all about composite beams. So this was plunge columns for the Shard, which we did many years ago now. Embedment plates for an ethane tank. Just the picture's not great, I appreciate. And going back to composite construction, what if stud welding is not an option? There are other options. So this is a Hilti HVB shown in the picture. It's like an angled cleat that you shot fire to the beam. Obviously doesn't need hot works. It doesn't involve getting a massive rig to site. You can often do it with the same gang that are installing, same people and kit that's installing the deck. But they're a lot more expensive. They're nowhere near as resistant as a welded shear stud. So all of those equations that I talked to you about at the start would not apply. You'd be looking at reduced values. So they're a good solution when you're in a problem. I don't know, you can't get hot works, you've got a small quantity, you can't get a rig to the area, you can't get power to the area. So there is other options, and that is just one of them. There's other alternate shear connectors as well, but the others aren't that readily available. And in reality, it's used as and when needed rather than as a standard. And that is me for today, talking. Hopefully that's been quite useful to you. It doesn't, as I said, it hasn't talked about the installation, because I know my colleague Richard Brokenshaw will be talking about that in the coming months. But if you've got any questions other than the ones we've had now during the presentation, then happy to hear them now.
One question, Jamie, that's just been posted. Can you use shear studs for thermally activated composite slabs where there are a network of water pipes embedded in the concrete? Or would this affect the interaction between the stud and the slab?
The answer to that question would be yes, you can, but you have to be very careful about the layout of the pipes. So the layout of the pipes mustn't interact with the shear stud positions, because potentially that removes concrete from the important location within the composite beam as such. There is guidance for that. I'm not sure that's on TGN, but if you've got a name, Dan, we can email that over to them.
Yeah, we have a name.
Yeah, as an AD note and stuff about positioning it, and it's basically making sure you consider the pipes as panels within the bays as such, and not running loads of pipes right next to shear studs. Might cause you some problems practically on some beam designs, so you may choose to maybe reduce the number of composite beams you use to make it easier to lay the pipes out, but they can be used, yes. I think probably the only last thing I'd say is, I know after this presentation, Pete from marketing will send round a Google form or similar, just to get feedback, which we really appreciate. It allows us to pick up subjects that we maybe should do in the future, and also feedback on the offerings that we give in terms of technical content, both on TGN, our website, through our design software, SMD Elements, or other the app that we have for the mobile phone, all the different stuff that we've got available. Any feedback or additional tools that people feel are useful is always good for us to have, because we can then see if we can help to aid your specifications in the future. So if you can feedback on that, and I think then also CPD certs come out on the back of that information. So I'll stay on here for a couple more minutes in case there's any other questions. Otherwise, thanks very much everyone for listening, and have a good rest of your day.
Thanks a million, Jamie.
Thanks.
Cheers.
Thanks, Jamie.
Thank you.
Jamie, one other question seems just popped in at the last minute.
Yeah.
Could you please clarify minimum reinforcement requirements for both double and single spanning slabs, and clarify whether you consider it suitable to reduce this where the crack width is not considered important? For example, a single spanning deck which will receive screed.
I can clarify that, but not verbally right now. I can see the question, and I will contact you directly or by email and send you some information on that. I think that's probably the best thing, because I don't have the information right to hand right now.
Okay.
Also, it's also in another presentation we do actually with regards to minimum reinforcement requirements, but I can steal some of the information from it and send you over an email. Right, 2 more minutes. If there's no questions, I'm off. Pete, how do we? Do you want me to stop recording? Yeah.
Yeah, please, if you can. Thank you.